Good evening, everyone, and welcome to the Auckland Bioengineering Institute's Tech Week event. I appreciate that there are many events happening at the moment, so it's really awesome that you have chosen to attend this one. My name is Diana Siu, and I'm the Strategic Partnership Lead of the Auckland Bioengineering Institute, or the ABI for short. So what I get to do is to introduce you to the ABI before I hand you over to our panel. Now, the ABI is one of two large-scale research institutes at the University of Auckland, and it was established in 2008. What a large-scale institute means is, a large-scale research institute means, is that we run independently of the faculties and we are focused on research. The ABI has a specific mission, and this is really about improving medical diagnosis and therapies for injury and disease through applying engineering concepts and innovation to medicine and human physiology. We are led by our director and co-founder, distinguished Professor Peter Hunter, really well known for his work on the heart, and our deputy director is Professor Maren Tawhai, known for her work around the respiratory system. The ABI is a postgraduate institute, and what this means is that we focus on training masters and PhDs. However, our academics also contribute to undergraduate teaching, and we run a summer scholarship program for undergraduates who are interested in research as a means of developing our pipeline of new students. We currently have 150 postgraduates, 60 academics, and 50 professional staff. The ABI has a long reputation for being an entrepreneurial and innovative institute as well. And since 2011, we have spun out 17 companies. We recently initiated Cloud9, our startup space, to support our early stage spin-outs until they actually find their feet. We are also well connected internationally, and within New Zealand, we host 2 national initiatives and a medical technology sector. These are the Consortium for Medical Device Technologies, known as the CMDT, and the MedTech Center of Research Excellence, which together links researchers, universities, industry, and government organizations across the country. Currently, we are working on a Trans-Tasman Biobridge to link MedTech innovation between Australia and New Zealand. So we have 4 key areas of research as indicated here. I won't read them all out, but suffice, tonight you will hear from 2 of these areas. Mark Billinghurst and Suranga Nanayakkara will talk about their work in AR/VR technologies, and Alys Clark on the models she has developed to describe pregnancy and how this can be used to support the health of baby and mother. Now, before I turn you over to our first speaker, some virtual house rules. So first, please use the chat function to ask questions throughout the session. And this will be moderated by Marketing and Comms Manager, Ruben Keeling. He will probably flag these questions after each of our speaker or at the end of the Q&A. If you, for some reason, have technical problems, send Ruben a chat message. So now do get in touch with us after the event if you want to learn more about what we do or about the research that you hear tonight. But on this slide, there are some ways for you to become part of the ABI community. So without holding you up any further, I will now turn this virtual platform over to Mark. There you go, Mark.
Thank you very much. Let me just grab the screen sharing from you.
I'll just start sharing. Yeah, cool.
And I'll put my slides on here. Great. So thank you, Di. It's good to hear from you, and it's good to see so many people in attendance. So what I'm going to talk about for the next 30 minutes is what we do in my laboratory at the ABI, which is a laboratory about empathic computing, and certainly the role of augmented and virtual reality in that. In my laboratory, we're really focused on communication. And of course, communication is really a fundamental human need. John Pierce wrote that communication is not only the essence of being human, but also a vital property of life. And there are many technologies that have been developed over the last thousands of years to help with communication. We can go all the way back to cave paintings or to carrier pigeons, all the way forward now to modern communication with mobile phones and social media. In my opinion, there are several trends that are happening in communication right now, and I'll talk about each of those briefly. So one is towards improved content capture. So moving from just seeing other people's faces to also sharing the places that they're in. The second trend is towards increased network bandwidth and using that bandwidth to have more natural, or be able to share more natural communication cues. And then the third trend is towards implicit understanding, or being able to recognize behavior and emotion. So first of all, content capture. If you go back 150 years or so, that was when the first photographs have been taken. And in the time since then, of course, we've evolved from still images to film to then live footage to being able to capture panorama images and so forth. So here's a short timeline of different ways of capturing reality. So in the 18th century, people were trying to create or capture reality by painting immersive paintings. And then the first photographs came in the 1830s, 1820s. Shortly thereafter, people were using stereo imagery, and the first moves in the 1870s. In fact, this little video clip here is the clip of the Roundhay Garden scene. Oh, it's not playing for some reason. Oh, that's interesting. Well, anyway, that's the movie clip that was one of the very first movies that were made in the 1888s. And then nowadays we can have the ability to share spaces. So you can put a camera on your head and you can live stream from that camera to a remote person. So instead of seeing your face like on a Skype call, they can see your view from what you're seeing with the camera. And there are now also many ways to capture 360 images. So there are a variety of cameras in the market that will not only just, that will also be used to stream 360. And here's an example of how you could use this to capture 3D spaces. So there's a company, Occipital, that sells a simple sensor you can add to your iPad. And when you move into somebody's place, you can scan around with the iPad and you can capture a 3D model of that surroundings. And of course, the most recent iPad has a LiDAR scanner built into it, so you can make a 3D model without even having to have an external sensor. So all this means that we're going from 2D static image capture, like with photographs, towards more immersive capture and creating 3D environments and also whole 3D spaces. The second trend is a rapid increase in networking speed. So when I first started using the computers in the 1980s, we had 2,400 more modems, and now my apartment here in Auckland has a gigabit fiber connection to it. So with that massive increase in network bandwidth, we can use that to send more realistic communication queues over the network. And we've seen the evolution of networking technology to go from telephones through to mobile phones to desktop video conferencing. And now with mobile conferencing, we can do things like live streaming on our phones, or even with applications like Periscope, stream live 360 video to remote people. And there's innovation in this space too. So Project Learn from Google, they're launching balloons all over the world to enable people to have unlimited access to a network, even in remote locations. So that means that we've gone from being able to share text to audio, and now with the very high bandwidth, we can share very rich video communications and natural communication cues. And then the third area is interaction technology. So, in the 1950s, when people were using computers, they started using punch cards or keyboards to interact with the computer. And then we've evolved from that to the mouse and keyboard, and now people are using speech and gesture. So here's an example of some pictures taken from very natural gesture interfaces, where you can combine depth sensors and you can recognize natural hand gesture. And you can also use physiological cues as well. So here's a product from a company Augmented that allows you to measure people's brain activity, or the Empatica band, which allows you to measure your heart rate. And so here's an example from Empatica. You can wear it the whole day, and it will measure your body temperature, your GSR, or your or skin sweating, and your heart rate variability. So this also changes how we interact with computers. So in the punch card era, we explicitly had to give computers commands, and now we've got computers that we can speak to or gesture at or even think about, and that will cause the computer to react to our implicit commands. So these three areas together form this overlap. So we have this bubble of natural collaboration, a bubble of experience capture and being able to capture our surroundings, and a bubble towards more implicit understanding. And where empathic computing is, it's right at the junction of this. So of course we all know what empathy is, and there's this really great definition from Alfred Adler saying that empathy is being able to see with the eyes of another, listen with the ears of another, or feel with the heart of another. And so what we're trying to do in my laboratory is trying to develop systems that allow us to better share what we're seeing, hearing, and especially feeling with others, so we can create deeper understanding. So I'll give you several examples of those, and you'll see how they progressively get more complicated and help us to share better our surroundings with other people. So one of the older projects we did was this one here, where we basically had a pair of smart glasses, and on top of the smart glasses you could put a depth sensing camera, and then you can stream the camera view to a remote person, so that person could then see what you're seeing. So in this video here, on the right hand side, you have a remote person who's watching the video, who's drawing on the video. On the left hand side, in the smart glasses or the augmented reality display, you can see that annotation now appearing in the real world. So this type of system will be very useful, for example, for providing remote guidance assistance or tech support, or enabling one person to be able to help another person perform a task in the real world. But there are some limitations, and one of the obvious limitations is that you're only able to share a limited amount of communication cues. So a little bit after that, we did another project where we married together an eye tracker with similar glasses, and also a pair of frames called the effective rear frames that could measure face expression. And we did this because we wanted to be able to share in communication eye gaze and face expression, which are very implicit communication cues you have in face-to-face communication. And we want to be able to share these remotely as well. So you can see a person here wearing all of that technology. They're also wearing a heart rate sensor as well, so you can measure their heart rate. And on the right-hand side, you can see what the remote person sees on the desktop. And most importantly is this green dot here and this red dot. So the green dot is the remote person pointing with their mouse saying, you know, move this object here. And then the red dot is the eye gaze of the person who's wearing the wearable system. And so the important thing about this is that you can now, the remote person can tell whether the person who's wearing all the technology is paying attention or not, because their eye gaze will follow his or her pointing information. So here's a video of the system working. You can see here what they're doing is they're completing a block assembly task, and the remote person is watching what the person with the head mount display is doing, and then using the mouse pointer to guide them to assemble the blocks. But as he's telling the person where to move the block, he can watch to see if the person's paying attention, because he can see their eye gaze movement. And of course, people always look at objects before they interact with them. So by doing that, we can share another communication channel over the remote video link. And with the studies that we conducted, we found that by sharing that eye pointing, that established richer communication with both people, and they reported that they felt more socially connected. And it changed the nature of the communication. So instead of having the person who was on the remote side having them to issue a command and wait for the person to move their hands or show they've understood the command, they can talk to the person and watch what they do with their eyes, and their eyes will always lead before they start performing gestures. However, there's one problem with this system, and that is that we're only sharing two-dimensional video. So more recently, we did a project where we could share 360 video. So the idea is that a person can wear a 360 camera on their head and live stream the view to another person who's in a virtual reality headset. And this 360 video sharing means that the remote person can now look in a very different direction from where the person who's streaming the video is looking. So you can see the setup here. You've got a person with an augmented reality display on their head, and also a 360 camera. They can stream the 360 view to a remote person who's in a virtual reality headset. and then the remote person can use their hands to indicate things on the video, and we send the hand gestures back to the person who's in the augmented reality display. And also it's very important now to be able to maintain some view awareness. So you can see in the bottom there, we've got a green square and a red square, and this shows each of the people where their partner's looking, so they know whether they're looking at the same view direction or not. So here's a video of the system working. In this case, we've got a person who's trying to do a maintenance task on a control panel in a power station. So it's a very complicated task, and he's stuck. So he's calling for some remote help, and he's using an augmented reality display plus a 360 camera. And then you can see here in his view, he sees this kind of ghost hand appearing that's pointing and drawing in the real world. And so it becomes a very natural way for the remote person to indicate what they need to do. And of course, there's also that green square there, and the green square shows the him where the remote person is looking. And on the remote side, we can live stream the 360 video, and so the person who's in the virtual reality headset feels like they're standing in the same location as the person who is performing the task. And so they can now draw on the video and make annotations and tell the person how to perform a certain task. And it turns out this is a very, very natural way to communicate. And you have this very high sense of shared presence, and you both feel that you're in the same location, even though you could be thousands of kilometers apart. So it becomes a very nice way to provide some remote expertise. However, this system uses quite a lot of technology. So in the last few months, we've been looking at how we could build a lower end version that could be used in more consumer-facing applications. So what we've done is taken the Jitsi platform, and Jitsi is essentially an open source version of Zoom. It's a desktop conferencing platform, and it's web-based, and so you don't have to download anything. It supports hundreds of users at the same time, and we created a 360 camera plugin, and so we can now live stream 360 video into this platform and support live 360 video conferencing. We've also added support for loading other content like 360 recorded video and still images. And we did this because when you have a 360 live stream video, the resolution of the video actually drops because you're taking that video and stretching it over a whole 360 degrees. So if you wanted to have somebody help you on a task where they had to point at a particular piece of machinery or something, then you may want to be able to load a still image that's higher resolution that you can then annotate and point at. So we put the system together. This is what the user interface looks like. It's very similar to using a Zoom call, but you'll notice here on the upper right-hand side, you've got this kind of warped video image, and that's the video that's coming from our 360 camera. Actually, we could have many 360 cameras if we wanted to, so we could use more than one if we wanted to. So here's a video of the system working. And you'll see one of the students there looking around, and then her friend joins, and he's now going to click on the 360 image. And then what he can do, we've got this live 360 image, and he can pan around the 360 image and look around the lab at night in this case. And so it's live footage coming from our lab. And then he can preload other images. So first of all, he's going to preload a video clip. So this is a video clip that's taken earlier in the day, and it's high resolution video now. So you can see the recorded video from earlier in the day from the lab. And then what he's going to do is he's going to load up a still panorama image, which is also taken earlier in the day. So here's the still image, and you'll notice that this is high resolution again still. So of course, this is very early beta. Oh, and also you could load up other still images. So this is another image from another location in our lab. So you could use this to give people a kind of virtual tour. So this is very early days, but one motivation for doing this is that it could be used for virtual tourism. So right now, of course, in New Zealand, the tourism industry is really suffering because international guests or visitors can't come here anymore. But with our system, you could imagine a tour guide live streaming from their location and walking through a vineyard, for example, or some other location and giving a live tour. And then periodically during the tour, they could load up 360 video or still images to show people pre-recorded content, and maybe at a particular location in the tour. If they're doing, for example, a tour through a museum, they may want to show a recording of people performing some sort of dance or some activity, or they may want to show a still image of what looks like inside an object inside the museum. So we're trying to explore how this technology could be used for tourism and other applications. And the great thing about this technology is that it's all web-based, and so it doesn't require the person at the other end to download any software or do any special installs. And then the person who's at the local site who's giving the tour, all they require is a 360 camera. But one of the limitations with this 360 work is that, oh, sorry, and this is what it might be like to have that tour experience. So you have a person with a 360 camera live streaming to you on the web, and then you'd have a guide who has a screen that they can then monitor who's connecting and watch what's going on, and you have a person at home who's able to talk to the tour guide and interact with them by remote pointing as well. So this is the set of features we're trying to set up, which we should have working in a couple of months, I think. But as I said, one of the limitations with this is that we're only sending 360 video, and you can't really move through the video. You don't get any sense of space because it's only a video. And so we're exploring now on how we can use 3D cameras and cluster them together to create 3D point clouds and perform 3D, create a reconstruction of a 3D space. So, you know, you can imagine that in the future you'd have some sort of small object you put into a location that will then capture automatically the 3D model of that location and stream it remotely. So here's a video of what this might look like. On the left-hand side is a God's eye perspective, on the right-hand side is a first-person view perspective. And you can see this is from the corner of our lab, and you can see the person can look around. And we've got a live camera feed coming in 3D, so now somebody's walking into the space, and so we can capture them on 3D live. And if he was to move any of the desks or any chairs or any objects in that space, then we'd be able to see that happening as well. There are some limitations with this. So you see many blue pixels, and the blue pixels are where you have occlusions or the camera can't see. And also that table in the middle is supposed to be a nice white flat table. It actually has a wave going through it because we need to calibrate our sensors. So this could be used, for example, for remote expert assistance in a factory or for other locations. And we can also take the cameras, instead of having them in a cluster like that, we can put them around the outside and we can capture what's in the space in the middle. So that's what this shows here. On the left-hand side is an augmented reality view. The person can see some ghost hand telling to move the object. On the right-hand side, this is a VR view. The person moves the object, and you can see the object moving in the VR view, and then it gets placed on the table again. And the person on the VR view is telling them how to position the object around a little bit. So we can use the same technology to capture spaces from outside in as well as from inside out. So you can see in our research we've had an evolution from 2D scene sharing to 360 and now to 3D scene sharing. And that's increased the level of immersion, improves the understanding, and led to much better collaboration. Once you've got those 3D captured environments, then you can do some more interesting things. And what we're thinking about is that, you know, sometime in the near future, we should be able to have a handheld device where you can walk into a space, push a button, and it'll automatically capture in 3D the space around you. And once you've done that, you could then share that 3D model with the remote person, and the remote person can go into a virtual reality version of that model. And so this experiment here we did a year or so ago was exploring that, how you could have a collaboration between somebody in the real world in augmented reality and somebody remote in a virtual reality copy. And in particular, when you do this, you have to think about how you want to represent the people who are going to be remote. So one way is to have a life-size 3D model of the person, and so you get a sense of space, and as they move through the VR copy of your space, they move through the real world. You can also, as it shows here on panel C, add some virtual cues to the person that might assist with the communication. So what we've added here is a virtual view frustrum, so we know exactly where the person's looking. And normally in a face-to-face communication, you can only see where the person's looking when you look at them. But in our version of the system, because we've got this view frustrum, we can see where the person's looking even when we're not looking at them. So here's a video of the system working. I'm just going to fast forward. Oh, here we go. So in this case, you can see this augmented reality view. We've got this pink head, which is the remote person. And here's the same thing in virtual reality. And then we've got these pink lines coming out from their head, and the pink lines represent their view frustrum. So as we work together on this task, which in this case is kind of a search and hide and seek task, we've got to try and find different blocks. We can see the pink view frustrum showing, in this case, that we're both looking in the same direction. And as the person moves closer, I can see their head coming into view. So of course, you can see from the setup here, one person's in the real world, one person's in a virtual reality copy of the real world, and they're able to collaborate together. But once you have a copy of the real world, you can do some more interesting things as well. And one of those is multi-scale collaboration. There's no reason why if I'm in a VR copy of the real world, I need to be the same scale. I could change my body to make it much smaller or much bigger and collaborate in different ways by doing that. So, and you could also change your view, so you could jump into the same viewpoint as the person in the real world and effectively inhabit their body and be able to see the world from their perspective. So here's a video showing what it might be like to change your body scale. Here's two people collaborating with our system at the same body scale, and they've got a little app where they can push buttons and drop objects into the real world. But then he can use the slider to change the scale. So now he's made himself really big, and you can see that the head of the other person looking really, really small. Now he can drop objects on a big scale, and this might help with multi-scale design, for example. And then he can also make himself really small, and then go into the nooks and crannies of the environment he wouldn't be able to as a regular sized person. So he's going to now change a slider back to 1-to-1 scale, and now he's going to move to a 10th body scale and make himself really small, and he goes down there, and if he looks up, he sees a giant head looking down at him of his collaborator. And this allows them to be able to collaborate more effectively on multi-scale tasks. And so that's a really great thing about having a virtual environment copy of the real world, is you can do a lot of different body scales with that. We also did some interesting work on separating out the communication cues from your representation. So you could imagine in the real world, if you are collaborating on a task and you can't see the person you're working with, and they could be pointing at something in the real world, but you can't see that because they're out of view. So you can see in this case, for example, on the left-hand panel, here's two people looking at a content on the table, and they can both see each other. But in the right-hand panel, one of the people has moved quite close to the shelf, and the person behind her is pointing at an object on the shelf, but she can't see that because he's behind her. So with this project, we call this a mini-me project, and the core idea was that we could create a small virtual copy of the person who's doing the communicating, and always put that in your field of view so you can always see it. So even when you can't see the person in the life-size view, when you turn away from them, you'll have this mini-me of them that's always in your view, and the mini-me will point at objects and convey some of the same communication cues as the giant person. And so when you lose sight of the collaborator, the mini-me appears and it can be pinned to your view. So let me show a video of this. I'm going to fast forward this a little bit because it's a bit long. So here it's talking about some of the limitations that you have with augmented reality displays, like the limited field of view. And so, but what we can do in our case is we can create a little miniature version person who's always in your view. So it's the miniature right there. So for example, the person's trying to point at this block, and the miniature appears and points at the block when they're out of view. And this is the case I was talking about before, one person's behind the other, and now you can see the miniature person appearing and pointing at that box of tea, even though the person who's controlling the miniature is behind her. And you can interact with that mini-me. So when you're looking at the person life size, you don't need to use it. When you turn away, that little miniature person appears and starts pointing at the same location in the real world as you are, as they were before with the giant person. So you can see once you start having copies of the real environment, you can do some interesting things about copying people's bodies and using those body copies to convey communication cues. And the last project I want to show is this project called On the Shoulder of a Giant, which continues that idea and basically means you have a little miniature copy of your remote collaborator, but you can attach that to a physical object, and now you can drag that object around in the real world to drag their viewpoint around. So in this case, she's got the miniature avatar attached to a tripod, and she's trying to get help with fixing a computer. So she can move the tripod around, and that moves the location of the remote person, and then then she can position him where it'll help her most, so she get a good view of the remote location. And you can see the little miniature avatar of the person appearing there, and there's a little view frustrum, and at the end of the view frustrum is a live video feed of what he is seeing. So we call this on the shoulder of giants because it feels like you can kind of pick up and move somebody around. So that's shown you some of the work we've been doing so far. I want to talk a little bit about what's happening in the future. And in particular, in the areas of augmented and virtual reality, there's a lot of technology trends happening. There's a trend towards advanced displays, towards real-time space capture, very natural gesture interaction, eye tracking technology. And the area that we're particularly interested in is using technology to capture people's emotions, and in particular, using EEG to measure brain activity. So there are some emotion sensing head-mount displays that are coming on the market now. So these are head-mounted displays that have EEG sensors in them, or physiological sensors for measuring heart rate or other sensory data. And this means that when you're inside the virtual environment, we can measure all this data and use that to enhance the collaboration. And really, as I said at the beginning of this talk, to some extent know how you're feeling and share that feeling with other people. So for example, here's a company called Lucid, and Lucid sells technology called the Lucid Link, and it's a foam pad that you can plug onto a VR headset to be able to measure people's brain activity in the front part of their brain. And then there's another company called NextMind. NextMind sell this set of electrodes, and you can put that at the back of the brain, and you can measure the brain activity at the back of the brain. And this is about $400 US, so it's a really reasonable price. So here's an example of using NextMind to play a game, and what the guy's doing is he's looking around and he's trying to destroy these aliens, and all he does is he looks at them and he thinks about destroying them, and then that sends a virtual laser beam or bolt or something out to destroy them. So he doesn't have to do any physical actions at all, it's just by concentration. So when you combine all these technologies together, you can create something that's called empathic teleexistence. And the idea of that is that you're able to be able to share more about people's emotional state that enables you to move from being an observer to being a participant. And from changing the communication from explicit communication, where you're always telling the person what you want them to hear, to more implicit communication, where you're looking at people's brain activity or face expression, and you're trying to infer from that communication behaviors. And this leads to perhaps potentially a more experiential collaboration where people feel like they're doing things together rather than you watching somebody's doing something. So the last thing I want to talk about is really new work we're doing on brain synchronization. So it turns out when you can measure the brain activity, then what you can do is look at how people's brains behave when they're doing tasks together. And over the last 10 years, there's been some really well-established phenomena of what they call brain synchronization. It turns out when people do a similar physical task, sometimes the EEG signals from the two people's brains become into sync. The phase of the signal becomes into sync. And when that happens, people report that they feel a lot more connected, and they feel like they're collaborating, working together better, and they could go into a kind of a focused state where they lose track of time. So one of the ways this happens is through a finger tracking exercise. You can see two people on the left here sitting down, pointing their finger at each other, and one person is supposed to move their hand, and the other person will move his hand to follow that motion. And while they're doing that, they get into a synchronized state, and you can watch the brain synchronization. So what we're trying to do is repeat that same thing in virtual reality, and see if by doing it in virtual reality we can actually enhance the amount of synchronization that's happening. So here's a typical setup. You have this shows the brain activity from two people. The black dots are where the electrodes are, and you have this heat map, and this is before they started the experiment. And then they do this finger tracking exercise, and this is their brain activity while they're doing the exercise. So you can see the person on the left has a couple of loops, and that means that the two electrodes that are connected together are now becoming in sync. And then when the people stop the activity, we can measure their brain activity again. And this time, remember, they're not doing any physical activity, they've stopped. And we see something like this. So this shows a lot of synchronization between both people. So what we're trying to do is reproduce those same results inside virtual reality, and it looks like we've been able to successfully do that, and then do some more novel things as well. So inside the virtual reality, this is what it looks like when you do the task. You basically point it to some other person and follow their hands as they're moving around. But what we can do is, because it's virtual reality, we can put one person inside the body of another and see if that makes a difference. And our theory is that if we're sharing the same perspective and same perception, we may feel even in more sync with the other person because we feel like they're inside their body. We've got some early results right now, but they're a little bit mixed. So we're trying to figure out how to redo the experiments and see if we can get a better result from those experiments. And then the last thing I want to show is a small video about how this might be used in sort of fun, interactive manner. So we've built the system called the Hyperdrum. And this is a drumming activity that measures the brain activity that people are drumming. And when they start getting into sync, then we produce some better visual feedback for them. So, excuse me, you can see up here is two people sitting across a table, and they can hit on regularly, it's called a neural drum, you can hit on a regular object as drumsticks.
Neural Drum is a VR drumming experience that allows two players to drum together while their brain signals are simultaneously measured. At first, you can set some daily objects on a table to use as drums. The player will use two drumming sticks to play the game. Both of the players will wear an EEG capturing hardware to get their brain signals measured from the frontal lobe. The data acquired will be streamed to the data processing system to enhance VR experience, depending on the player's collaborative performance. We designed a software to calculate the phase locking value, which is an index of neural synchronicity, for the FP1 and FP2 channels of the theta band from both the participants. When synchronization between two players is low, the camera will be more clear to do so, whereas when synchronization is high, the vision becomes more obscured, with each point cloud eliciting higher particle effects. We logged and analyzed the user's brain signal.
So I'll stop that, but so basically what happens is that as you start drumming and you start becoming more in sync with your partner, you get a lot more visual effects happening as well. So what I've shown you today is this talking about this trend in communication towards empathic computing. And then we're giving you several examples about how AR and VR can enable enhanced empathic experience. So for example, allowing you to look through somebody else's eyes, to share your space and surroundings, and to support annotation and communication in really interesting, unique ways. And then there's many directions for future research. And I've shown you an example of what we're doing with our EEG studies and looking at brain synchronization. So that's everything for today. If you have any questions, I think there's going to be a quick question and answer session after the next two talks. And I'm also happy to answer questions over email. And if you visit our website, you'll see many other ideas and other projects we're doing. So thank you very much for your time.
Thanks, Mark. Alys, are you there?
Yes.
Great. You want to take over?
Hi, everyone. My name's Alys Clark, and I'm going to tell you a little bit today about a virtual pregnancy that we're developing here in Auckland. And the point of the virtual pregnancy is really to understand what matters for a healthy pregnancy and how we can improve pregnancy health by creating virtual organs, which I'll talk more about in a second. So lots of things contribute to a healthy pregnancy. There's genetic factors that can affect the growth of the baby when mum is pregnant, the environment of that baby, what mum eats, whether mum smokes or drinks, and other factors relating to the mother can kind of add up together to cause problems in maybe cellular function and tissue function in the growth of the baby. And that can all add up to problems with how the organ systems within that baby develop. So it's a complicated thing, a healthy pregnancy, and there's lots of contributors to a good outcome. What can go wrong? Well, some of the key things that can go wrong, the most serious being stillbirth, where the pregnancy just can't continue. Fetal growth restriction, where baby doesn't grow as well as it should, which I'll be mostly talking about today. Preeclampsia, which significantly affects the mother and can cause very high blood pressure in mum. And issues with pregnancy can lead to problems long term, so potentially for both mother and baby. So things like issues with the child's cardiac function later in life. So returning back to a fetal growth restriction, which is a reduced growth rate of the fetus, which prevents it from basically meeting its potential growth. It's one of the greatest risk factors for stillbirth, and we don't yet have an effective treatment. So often babies are born early and they're at risk of the subsequent kind of issues that happen with premature babies. One of the key ways that we try to identify growth restriction is by taking measurements of the baby using ultrasound at various stages through pregnancy and trying to ensure that that baby is growing at the rate that it should do. But unfortunately, we're actually still missing a lot of these cases. So more than 50% of cases of fetal growth restriction are actually not detected prior to birth. So we're not doing a great job clinically of detecting those problems just yet. So why do we miss them? So at the end of pregnancy, you can quite clearly see when a baby isn't as big as it should be. But often the problems in pregnancy start very early and very small. They're not very visible to the standard ultrasound imaging techniques that are taken during pregnancy. The picture on this side of my screen, the right-hand side of my screen, shows a very close-up view of the blood vessels in the placenta, which is what feeds baby, essentially sits between mother and baby and provides the baby with its oxygen. On this side, the normal pregnancy has a lovely branching blood vessel structure. A growth restricted pregnancy has much longer, less branching blood vessels, and that actually impacts how much oxygen the baby can get to grow, but we can't really see this level of detail in ultrasound. So that's one reason that we miss these issues. So, like I mentioned, we can't often see those really kind of small scale things changing in pregnancy. And that's because we're limited to imaging like ultrasound because we want to avoid radiation. There's a picture here of a CT scanner. So CT is a really great way in the clinic to view body in high resolution, but it gives high radiation doses. So we want to avoid that kind of thing in pregnancy, which means we're normally limited to relatively low resolution imaging. We want to be non-invasive, so we don't want to be sticking probes in a pregnant woman or doing any tests that are unnecessary. And often the non-invasive ways to assess health are not really specific to the problem that we're looking at. We're not always looking at exactly the right place in the body. And the other issue with detecting problems in pregnancy is when we do look at the fetus normally with ultrasound, it's infrequent. It might happen at in early pregnancy, maybe in 10 weeks pregnancy, around about 20 weeks of pregnancy, but in a lot of pregnancies, it doesn't happen more than twice. So we're just not getting the whole time course of what's going on. So because pregnancy is so complicated, there's a wide range of science going on to try and work out what is actually happening to pregnancies that suffer from fetal growth restriction, what could be the causes of it, what could be possible treatments for it. And that science covers a great range of space. So from studies of genetics of mother and father and baby, looking at studies of cell behaviors for key parts of the system, for example, in the placenta, which feeds baby, looking at how blood vessels and tissues function, and then looking in the clinic or in the body at measures of how the baby is growing or how the placenta is functioning. So, oh, I'll just go back a slide if I can. So yeah, so there's lots of science going on, but there's no real way to link together data acquired in these different scientific disciplines. So how do we link together somebody's genetics to the way that a baby grows in a kind of mechanistic functional sense? It's not completely clear how to do that when we're collecting such different data from such different disciplines. And so if we did know more about what was going on in pregnancy, we could potentially treat things like fetal growth restriction, but we really need to use medications for treatments or to prescribe treatments to try to cure problems. We need to have a real understanding of the risks and benefits of providing those treatments. And in pregnancy, there's big knowledge gaps. We don't, a lot of drugs are untested in pregnancy, and it's very hard to get a clinical trial going in pregnancy. So it's a complicated thing to test for pathology, to do the science around understanding what's going on in pregnancy complications, and then subsequently to treat issues if we know how to do that. So that kind of leads to the work that I do, which contributes to what is called a virtual human. So what if we can take everything we know from the science about pregnancy, from different disciplines of science, right through genetic work, through to kind of clinical studies, and what if we can create a virtual human that behaves like the real human in terms of physiology? So its lungs breathe like real lungs, its heart beats like a real heart. And could we use that virtual human to allow us to take a closer look at how the body works, not only in pregnancy, but across a lifespan? So this virtual human and the context that I work in is kind of led in a project called the Physiome Project, which spans all sorts of different areas of biology and physiology. And what we're trying to do is create computer-based virtual representations of everything from proteins through cells to tissue and organ systems. So this kind of virtual human concept allows us to take measurements from different scientific disciplines, like I talked about before, and actually try to link together those different measurements. So if you have experimental measurements of cell behaviors, for example, and that cell is part of the fetus or the placenta, if you perturb the behavior of that cell, how does it impact the whole organ? And what are the mechanistic links between abnormalities at this kind of scale to what we're seeing clinically? What that then allows us to do is test hypotheses regarding biological function. So do some of our hypotheses about what is really happening in a problem pregnancy make sense in a mechanistic physical sense? And ultimately, hopefully it will allow us to predict the impact of drugs or therapies. So to conduct virtual clinical trials where we can basically use this virtual human concept to refine and design real clinical trials, so that we need fewer kind of false starts, fewer participants, or better classified participants based on what the virtual human would do in response to those therapies. So the virtual pregnancy, which is the space in which I work, takes all of those concepts and tries to apply it to what makes a healthy pregnancy. So we're looking at developing new ways to measure the anatomy of pregnancy, to look at the organs and the parts of the body that are really responsible for healthy development, and to look more closely that anatomy. We're looking to provide new insights into things like cell behavior, so to look into really deep into the physiology of pregnancy and to understand how different conditions can impact on how our cells function and grow, because of course pregnancy is a growth from 2 cells to a whole baby over 9 months. We're looking to develop new tools to analyze data. So if we have clinical data or physiological data, how can we analyze that in the most effective way? And new ways to image function. So going back into the clinic, looking at ultrasound and looking at those low resolution imaging techniques that we can use in pregnancy and trying to interpret them better. So I'm just going to give a couple of examples of how this virtual pregnancy concept works, and then tell you a little bit about where we're going in the bigger picture. So I mentioned before fetal growth restriction, which is an issue where the fetus doesn't grow as well as it should. Primarily that's an issue with the fetus not getting enough nutrients and oxygen, so not being fed as well as it should be. And the placenta, which I said before sits between mother and fetus, is responsible for delivering the nutrients and the oxygen and all those good things that baby needs. So the fetus is connected to the placenta by the umbilical cord, and the placenta is a complex tree structure of tissue and blood vessels, which is fed by mother's blood. So oxygen-rich blood comes from the mother's uterus, bathes the placenta, and the placenta gets the nutrients from mum that it needs to grow. So in fetal growth restriction, and in any pregnancy actually, we're able to analyze what the placenta looks like after birth, which is a great benefit for understanding how it functions. So we get the end point, we get to understand what that placenta looks like and how that might have been contributing to the growth of baby. And we know that in fetal growth restriction, the placenta is smaller, so around 29% smaller in volume. It's thinner, so it's kind of a discoid shape, and there's around a 21% decrease on average in the thickness of the placenta. There's less blood flow to it, and it has a poorer branching of the blood vessels, like I showed in the previous slide at really high resolution. So can we use our virtual pregnancy to understand what is the difference between a normal and growth restricted pregnancy? And perhaps importantly, is there somewhere on the spectrum between normal and severely growth restricted where we start to see dysfunction of the placenta that might be clinically significant, that might have an impact on the fetus's health, and both before it's born and long term? So what we do is we take data from these placentas after delivery primarily, but in theory you could take data from ultrasound taken during pregnancy. And that data might show us the branching of the largest blood vessels on the placenta. We might be able to take the placenta and put it into high resolution imaging machines, in this case a micro CT machine, and actually look in very fine detail at the blood vessels in the placenta. And we can take that structure and map that structure onto a computer representation of those blood vessels in the placenta. We can then simulate using the laws of physics, so predict using the laws of physics how hard the fetal heart has to pump to get blood through that placenta. What is there areas of the placenta that get more or less blood to them because of that anatomical structure? And importantly, we can predict the kind of things that we can see in ultrasound. So what do the patterns of blood flow look like in the umbilical blood vessels, those largest blood vessels that we can actually see on ultrasound? So in this case, we've done that for 2 real placentas, 2 real normal placentas shown on the the top of my screen. One of them is a nice round placenta imaged using micro CT imaging. The umbilical cord kind of enters the placenta quite near to the middle, and the branches of the blood vessels are quite even and quite organized. On the other hand, this placenta, the one on the right-hand side of my screen, the umbilical cord enters that placenta right near the side, which means there's quite long vessels that have to feed to the edge of the placenta and a less regular branching structure of those blood vessels. When we simulate how that placenta functions, although both have a normal blood pressure, the fetal heart has to pump equally hard, basically, to get blood through each of those placentas. That nice symmetrically structured one, here the picture shows blood flow through the placenta to different regions of the placenta, where red is high and blue is low. You see that the placenta gets quite an even distribution of blood flow all the way through it, that nice symmetrically branching structure. Whereas the one on the right-hand side has a kind of patchiness to it. So there's these blue spots through the structure, and that is actually parts of the placenta where the fetal blood is not being delivered. And that means that's part of the placenta where oxygen can't effectively get from maternal blood into the fetal blood and feed that baby. So while on the face of it, these are both normal placentas, the one on the right-hand side is potentially more at risk, because if there became any more patchiness or any more issues with that placenta, it would, according to our virtual models, stop functioning as efficiently as it could. So this is helping us to distinguish between what is normal, really normal, and what is maybe an at-risk structure. And can we start to look for that in ultrasound in the future? So another area of our research is trying to take some of these virtual placenta models and get into the lab to try to understand how the structures that form that placenta could impact on its growth. So I mentioned before, in fetal growth restriction, the blood vessels are usually longer and thinner, and they have less branching than in a normal pregnancy. And we can represent that kind of difference in blood vessel branching structure in our virtual models of the placenta. And we can zoom right in on the capillaries, on the smallest blood vessels where the development is actually happening, and predict whether a normal or a growth restricted pregnancy might have been exposing those cells to different environments, the cells that want to create new branching blood vessels. And what we found when we went into the lab is when we did expose the cells that are typically found in those small developing blood vessels to the conditions of a growth restricted pregnancy, those cells behave differently to when you expose them to the conditions of a normal pregnancy. And actually the difference in the behavior between the cells exposed to normal pregnancy compared to growth restricted pregnancy conditions is indicative of a phenotype of reduced vascular branching. So potentially there is an interaction between the structure emerging in a growth restricted pregnancy where there's not much vascular branching or blood vessel branching, causing ongoing problems where things get worse as the pregnancy continues. So potentially that's something that we need to investigate further as an indication of something not going quite right in a pregnancy. So the next example I'm going to talk about is considering the uterus. So as I've touched upon before, there's kind of two sides to a pregnancy. There's the fetus, which grows within the uterus, and the uterus itself, where mum's blood is being delivered, that oxygen-rich blood, to feed the placenta. And I mentioned before, the placenta has quite a complex branching structure. My cursor is now sitting on on the placenta, which attaches to the uterus and is fed by the blood vessels of the uterus. But the uterus also has quite a complex branching structure. It's a little bit less accessible to measurement. We can't look at the uterus after pregnancy anywhere near as easily as we can the placenta. But we have the same kind of situation. We have a really complex blood vessel branching. And when we take ultrasound images of the pregnant uterus to understand the health of a pregnancy, we're targeting our imaging. So this is an ultrasound probe on the largest blood vessels that feed the uterus. And there's all this complexity downstream of where we're taking those ultrasound measurements. We simply don't have the resolution in ultrasound just yet to actually see the complexity of what is happening in the uterus and in the placenta itself. So what do we see if we don't see all of that complexity? What we see in the biggest blood vessels of the uterus is a measurement of blood flow. In those big blood vessels, we can see that with a mum's heartbeat, there's an increase in blood flow and then a progressive decrease, an increase again, and a decrease. And in a normal pregnancy, that's quite a smooth curve with quite a small bump at first and then a gradual decrease. In very early stages of pregnancy or in a growth restricted pregnancy, sometimes we see this big increase in blood flow followed by a rapid decrease and then a bump and then a gradual decrease. And this bump here is called a notch. And that is thought to reflect a abnormal development of the placenta right downstream of the uterus. So when we started looking at the uterus and how the uterus functions, I think it's important to kind of talk about what everybody's kind of thinking about those notches and those things that we're measuring in ultrasound. So we had a lot of conversations with an obstetrician that we work closely with. So somebody who's actually looking day to day at those ultrasound indices. And they wondered, what were they actually seeing? Why don't the indices always correlate well with fetal health? So while sometimes you see those abnormal features in the ultrasound, it's not always there when there's a problem. And sometimes it's there. Sometimes it takes quite a lot of a problem before you actually see those indices. We've had conversations with imaging specialists who are really interested to know whether they can see more of the uterus. Do we really need to be looking only at those biggest blood vessels? Are other blood vessels within the uterus important too? And then the physiologist would be wanting to know what is going wrong in abnormal pregnancies and what is actually driving problems with the uterus. So together we can start to answer questions about what do we currently know about how the uterus functions in pregnancy, and can our virtual models give us more of an understanding of what's going wrong when problems do arise. So actually those ultrasound images that I showed you just before, their interpretation came from a virtual model of the uterus, so a virtual representation of the uterus based on the information that we had about the anatomy and function of the uterus in the 1980s. And what that model did was it said there was a large artery that fed the uterus, and then all of the complexity and structure, all those connected blood vessels, the maternal blood vessels, the mother's blood vessels feeding the placenta, and the placenta itself were not too important to represent anatomically in this virtual model. And just some of the arteries which changed the most dramatically were assumed to dominate what we're seeing in ultrasound in both normal and abnormal pregnancies. So all of this complexity was ignored in that virtual model, in part because we didn't really know back then what that complexity looked like in detail. We couldn't image it very well. one thing that we've learned since then in the 2000s is actually all these connections between the arteries and the veins in the uterus. There's a very complicated blood vessel network. So we thought, well, what if we incorporate all of that in our model, our virtual model, and you don't need to understand much about this picture other than we've added a whole extra level of complexity to that model, which represents what we now know about the anatomy of the uterus and all those connections between arteries and veins that you see there in the uterus. And actually, when you include that complexity, what you can see with these virtual models, and again, the detail of the graphs is not too important, but the anatomic connectivity between arteries and veins, including all of the upstream vessels right to the uterine arteries and including specifically how the placenta functions. Our virtual model now shows that in fact, abnormal waveforms or abnormal ultrasound indices can be predicted even if there's not a problem with the placenta. So the placenta can be growing absolutely normal, but if there's something wrong with the uterus, you can still produce abnormal waveforms. And conversely, if the blood vessels in the uterus have adapted to the pregnancy appropriately, your placenta has to look pretty bad before you see problems in ultrasound. So potentially the reason that we're missing so many problems in pregnancy is because the uterus itself might be obscuring our view of what is actually happening at the placenta. So maybe we have to look a little bit more closely at the placenta to really make predictions about whether a pregnancy is going to go on to develop fetal growth restriction or not. So now I'm just going to turn a little bit to the future. I've talked about two components of the system, mum's uterus and the placenta, which feeds the baby, and those are very, very critical components of the system. But there's actually two people involved in a pregnancy, and like I touched on earlier, the problems that can occur with a pathological pregnancy, so with problems in pregnancy like fetal growth restriction, can be ongoing. There can be issues for a lifetime for that baby in terms of their heart, because they haven't developed, their heart hasn't developed as it should because they haven't grown as well as they should. There can be issues with other pregnancy pathologies with mother's cardiovascular system. And so we kind of need to step away from maybe looking at virtual organs, so just looking at the uterus and the placenta, or the uterus and placenta together, and actually start thinking of the system, which is much more complicated when it comes to developing these kind of virtual representations of the body, but it does need to be done. So when we're looking at that system, we can then turn to more advanced imaging, which has really been emerging over the last 5 or so years, and which we can now do here in Auckland. So on this slide, I'm showing an MRI image as you move through a pregnant woman's uterus. You can see the fetus there, and the placenta is kind of the fluffy gray matter at the top of the fetus. With MRI, we can actually create maps of blood flow and oxygenation of the placenta, and actually of other fetal organs too, which we can start to try to represent in our virtual pregnancy. So a virtual model of the placenta, which predicts how blood comes from mum to baby to feed the baby, and how blood comes from the baby's circulation to pick up that oxygen from mum's blood. And so with this kind of advanced imaging of the whole system, we can start to look at how we can really represent virtually in much more detail how mum and baby interact in pregnancy. So that's kind of zooming out and looking at the system. The other thing that new technologies are really enabling us now to do is to look more closely at the system. So this movie here is a cut through of a chunk of placenta where we've injected the blood vessels with contrast, so dye that enables us to see them more clearly in micro CT imaging. And you can really see from this video as you move through how complex that blood vessel structure is in the placenta, how much of it there is. And that's really because it needs to be complex. There needs to be a really big surface area to feed the baby with oxygen. But we're only really just starting to be able to image the placenta in this way and to really get a grasp of what that means for how it functions. And to really understand how that functions, we need to be creating these virtual representations of the organ, because we'll never be able to see, or at least for some time, we won't be able to see this real detail and its impact on function in clinical imaging. So just to summarize, a lot changes in pregnancy. In 9 months, a whole baby is basically grows in mum's uterus. And we really, to be able to detect and treat problems in pregnancy, we really need to improve our understanding of what is going on, what is a normal physiology of pregnancy, what is abnormal, and where does that line sit between normal and abnormal. And so our work on the virtual pregnancy is really bridging that gap between the clinical science and different scientific disciplines through biology and physiology to really help to identify what matters the most for a healthy pregnancy, with the hope that we'll then be able to do a better job of developing, for example, ultrasound strategies that look specifically at what matters most rather than what is the easiest blood vessel to find, or what is the or just taking kind of linear measurements of growth, which don't necessarily in the early stages of pregnancy indicate that a problem is going to emerge later on. And just as a final slide, to acknowledge my funders, our funders, and Joe James, who works in obstetrics and gynecology at University of Auckland and co-leads this research. Without her, none of this is possible. And our group, which is co-located at Auckland Bioengineering Institute and in obstetrics and gynecology, all of these faces here, as well as Ali Majulili and Peter Stone, who have really played a really great role in the MRI studies and are leading great research in that area, as well as a whole bunch of researchers that work with us from overseas and around Auckland. We couldn't do any of this without contributions from many, many groups in lots of different disciplines.
Hi, thank you for joining our ABI Tech Week seminar. The inspiration from what I do actually came from a simple sound that I heard almost 20 years ago. It was this sound. Yeah, it's a simple knocking sound, right? And I actually wondered who's by the door when I heard this first time. However, it turned out to be that this was Yahoo Messenger sign-in sound back in early 2000. Initially, I felt a bit stupid. What the hell, I didn't know about this simple thing. But come to think about it, what am I supposed to do when I hear a knocking sound? Am I supposed to look at the door and check who's by the door? Or am I supposed to look at the screen and check who's online? So, more I think about it, it became pretty clear to me that there is a mismatch between what technology has to offer and what we do humans. And there is a gap. And my lab that was set up in 2011 is pretty much focused on how do we bridge this gap between the technology and the humans. Let me give you a simple example. Suppose I want to move a few photos from my phone to someone else's phone. What do we do? Email, Dropbox. Maybe there are some apps such as Bump, use them, or if you happen to be on the same provider, maybe AirDrop, those type of things. However, if I want to give something that's in my hand, something tangible to someone else, I don't even have to think, I just grab it and pass it on. So, the question is, why two different ways of interacting? When it's tangible and physical, it's simply taking and giving over. When it's digital, when we can't touch it, then suddenly we have to learn a whole new set of new interactions. I wanted to figure out a way so that you can move digital media across devices as if they are tangible. So here is a project that I did in 2011 at MIT, where you could simply grab digital content as if it's physical and move them across devices. So this example here, you see a phone number on a web page. I just grab it and drop it to my phone. So you can call that number. Here's another example. I have a movie. I want to give it to my friend. Just take it as if it's tangible. Pass it on to the other person. So the actual data transfer happens through the cloud. But the point is, the way we interact is pretty simple, and it's very much like the way we would do it in natural way. So that's one example. Let me give you another example. I'm sure pretty much all of you have a smartphone, and I suggest you to take it out. We are going to do an experiment. So open your phone and go to a screen that you have so many app icons. The challenge is, hold the phone with one hand. Don't look at the screen of the phone. Look straight up and try and open one of your favorite apps, WhatsApp, Facebook, whatever it is, without looking at the screen. If I had been there, I would have asked you to raise your hands if you had gotten this. I'm sure most of you found it difficult. Even though we carry this pretty much all the time, we have no idea where the things are. In contrast, if I ask you to touch your earlobe, touch your nose, touch your forehead, touch your elbow, you can do it without thinking, right? Why? We have this amazing ability called proprioception, that we have a almost intrinsic understanding of where our body parts are, which, by the way, doesn't extend to these smart devices. So the question is, why design the smart device that way, that doesn't leverage on these amazing capabilities we have? So we worked on showing the value of rethinking of the form factor and the body integration of smart devices. We thought, okay, let's take ear as an example. We got a bunch of people into the lab and asked them to touch various parts of the ear. Earlobe, top of the ear, middle of the ear, and we looked at the precision. As you can see, if it is two location, it's very accurate, but if you want people to touch many locations, the accuracy goes down. So what that means in terms of designing an interface is that you could design here as a 3-button interface. As you can see from the second image from the left. So if you had 3 buttons, what this also tells you is that there's very high accuracy, precision among people touching earlobe or top of the ear, which means you can have tiny buttons. And in the middle of the ear, people vary among themselves. So you need to have a wider button to capture this variance among people. And we actually built a proof of concept prototype, which we call the earput. And with that, you could think of that as a simply an input device that you can seamlessly integrate without having to think. It's not like I get a call now and then I take the phone like that and then it just ruins this conversation. Instead of that, I can just do this to cancel the call. Or I might be going for a job. I need to increase the volume of my music. Again, changing the gate, staring at the viewfinder and having to change that. That's not a good thing. Instead of that, I could be just tapping here to increase the volume as I run. So here is a proof of concept prototype, a functional prototype of the earput concept. Okay, so these are 2 examples. Maybe let me give you a third example. Another natural capability that we have is really pointing at things and asking questions. Whether we are young or old, we always like to ask, what is this? What is that? It's a very much a natural behavior. But the point is, this doesn't extend to smart devices. I'm not sure whether you have seen how a blind person would use a smartphone. It's almost like taking the phone without access to the viewfinder. They need to do this voiceover, whatever they touch gets spoken back to them. Based on that, navigate to icon and then open an app and try and take an image. That's very cumbersome. When you get a chance, try and do that. Try and close your eyes at some point and try and take a picture. It's very hard to frame something because the camera is somewhere here and you have no proper coordination what the camera is seeing and unless you pay attention to the viewfinder. So instead of going through that route, we were like, can we leverage on our natural behavior of pointing and asking? We developed a project Finger Reader. Basically, it's a camera worn on the index finger. That was the initial concept that allows a user to simply point at something. The camera sees what the user is pointing at, and our AI algorithm can recognize this visual information, convert that into audio. For a blind person, this is very useful. They just have to simply point at something and the camera sees and they hear the information. Here is a demonstration of our very first version. Here you can see a blind person walking into a library and from a whole aisle of books able to pick the book she wants, simply moving the finger along the book and hear what the book title is about.
History of reading. During the next 10 years.
As you can appreciate, there's a huge amount of image segmentation work, computer vision work has been gone into this, as well as dedicated hardware design. For me, that's not the critical part. The critical part is really packaging the technology in a way that it helps us, or it's rather building upon what we are naturally good at doing, pointing and asking questions. So basically it has a smart camera, AI engine, and the audio interface. With this you can develop so many different applications. It could be reading tool, it could be a currency note recognizer that we developed for Singapore currency. It could be product recognizer or even a language translator. Or it could be something that can read things like restaurant menu. Pretty much giving an independence to a person without sight. And it doesn't stop there. The possibilities are a lot more because, again, it leverages on our natural behavior. We actually, just to show that there are use cases beyond blind people, we built this creativity tool for anyone to merge the power of digital devices and the beauty in nature. Simply you can point at things in nature, flowers, leaves, extract nice colors and textures and move them as digital paint, as you can see from this video. So we have been working on this project for now about 6 years, and really the other important factor of doing what we do is making an impact. We don't want to just stop creating a nice prototype and writing a nice research paper and doing a nice demonstration and stop there. We really want to bring things out to the hands of the people. So we have been iterating and trying to make it much more practical, and we found that the ring form factor is a bit hard. You can only make it so much small, still it's not going to be practical. So what we did was we redesigned the whole form factor into a smart headset, a bone conduction headphone, so that the ears are still open for you to hear the surrounding sound, and you hear the audio from this through the bone conduction headphone. Since there's a headphone, we put a camera on the headphone itself. The camera still sees the entire view that you are looking at, but we have a deep learning algorithm that recognizes the fingertip. So as you put your finger up here, trying to extract information from this entire scene, the algorithm just probes that region and try to understand what the information is in that region and convey that to you. And with this, it's a lot more practical for a blind person, and not just then. This is not just the visual recognition stuff. They can also use this to receive calls, get navigation instructions from their phone. So basically, it becomes a much more practical utility. Here is a little video of the latest work in the finger reader.
Trigger the camera.
Okay, so if I pointed at something, like let's see if it can read this. It's come a long way, but they believe they can make it even better.
Honey, squeeze me. Text found as poems in the waiting room.
Amazing. Poems in the waiting room, that's exactly what it is. So how important is technology like the finger reader for the blind?
Incredibly important. It's bringing technology innovations into the mainstream for them. We really thank them with our heart to say thank you for doing this, because what it's actually doing is making life one of choice for them.
This innovative technology that's now being worked on in New Zealand is not just helping people to see. A trial in Singapore is looking at helping children with dyslexia read. The team's also hoping it can be used as a translator.
My hope is it will really become a device that blind people use on a daily basis.
So Dan, you haven't tried the finger reader yet?
No, I haven't, but I'm quite intrigued to see what it's all about.
For Daniel, seeing is believing. Pop that on your head, and then what you do is you put this on your index finger.
Facts found as seafood.
It is a magazine about seafood.
That's quite amazing. It sort of goes through and lists off all the sort of top headlines and stuff like that.
Coming to a cafe or a restaurant can be a bit of an issue.
Oh, definitely. If I could just sort of point at a menu and it reads out to me, that'd be amazing.
So these are actually examples of our main concept, which we coined as assistive augmentations. What that means is, the way we think about what we do is, it's really about harnessing the full potential of technology by designing very intuitive interfaces with the idea of us just be able to use them without us having to change what we do, the way we do stuff, but rather the technology adapting itself to fit into us. So that's the main thing. It's really intuitive because we don't have to change the way we do stuff. The technology changes and this very powerful stuff gets packaged and the user interaction becomes simple and seamless. There are multiple applications once you do that. It's not just assistive technology focusing on people with disabilities. It has a wide spectrum, all the way from people with specific needs, people with sensorial or physical impairments, helping them to substitute for a capability, all the way to augmenting human, to allow them to do things beyond what they think they could do. So finger reader, for example, it could be an aid to substitute for the lack of visual capability for a blind person, but on the other extreme, it could be a translator for a traveler, or it could be a way to detect what's a counterproduct or what's the original just by being able to zoom into micro patterns and recognize. So that's sort of the spectrum. And we think about assistive augmentations with three different considerations. The first one is the integration. We think about in a very explicit way, either how do we integrate the technology with the body so that it becomes part of the body or rather extension of the body, or we think about how to integrate that into our behavior so that it becomes just part of the behavior. So integration is a key consideration. The second part is understanding the user. Focus on really understanding the user's intent, their physiological behavior, so that you can provide the right input or right assistance at the right time. The user still should feel the agency, they are in control. It should not be too much of technology trying to get in the way and trying to control them, or it should not be where I have no idea how to use it. So it's a nice balance where you still feel, the user still feels in control and feels like technology is providing the right support at the right time. The third consideration is enhancing. So it's always with the idea of either strengthening an existing capability or providing something that wasn't there, really extending abilities, creating augmented human. So let me now go to several more projects just to substantiate these ideas. This is gym soles. It's basically a smart insole that you can wear that can sense your body pressure and provide vibrotactile feedback to your feet. And with this, we found that you can do several things. In this particular case, it can provide vibrotactile feedback for you to do full body exercises like squatting or deadlifting with the right posture. Because of the vibrotactile feedback, subconsciously the users are able to adjust their posture. We actually ran a study comparing the body posture with motion tracking system of trainers as well as very novice users, with and without this feedback, and we found that with this feedback you do get better in your posture, and which is important especially to avoid certain damages to your joints and your body. Here is a short video about gym soles.
We present GymSoles Plus Plus, an extended reality approach to improve the body posture when performing squats and deadlifts. We develop a flexible wearable insole with 8 vibrotactile motors that provides haptic feedback on the center pressure of the body. Additionally, we developed a visual feedback system by using Google Glasses. It has shown that translating hidden information on the center of pressure back into reality can assist users in maintaining a correct body posture when performing squats and deadlifts.
This is Chewy. It's a smart chewing gum that allows users to simply put it in their mouth and interact by biting on it and rolling and touching it with the tongue. It's really an interface that allows you to do hands-free, eyes-free interaction. You don't need to delegate your sight to it. You don't have to delegate your hands. Imagine if you're riding a bike and you want to cancel the cord. How would you do that? Or someone in a wheelchair, fully paralyzed. Can they control the wheelchair on their own? So there are really nice applications, but this needed us to really think about what size makes sense, what shape makes sense, what are the safety considerations. After going through so many iterations, we have a functional prototype that allows somebody to simply put it in their mouth and use it as a controller for any digital device. Here is a short video of Chewy.
By using hands-free input operations, you will be able to shuffle through your playlist while riding.
The club isn't.
He said, let's get out of this town, drive out of the city.
Also, it can help you during your office work or presenting your projects to an audience. Chewy aims to unveil novel users' interactions, allowing more intuitive hands-free operations.
Another project, Lemo. The idea of this is being able to walk up to any object, any passive object, be it a wall, door, table, whatever, or your own body. Can you interact as if it's a digital surface? Can you do touch interaction? Or grab any pen, any pencil, any passive pencil, and can we use them as a digital stylus? It turns out that you could. We managed to build a system with just a simple IMU mounted on fingernail, and with a properly designed AI backend. You could recognize the motion and turn any passive surface into a digital surface where you can do touch-based interactions. And this video really demonstrates all the capabilities.
Devices and turn the finger itself into an input device. We realize this with a nail-mounted IMU. It captures the rich information of finger movements, and the activity information could be extracted with AI algorithms. Specifically, our system supports 3 different interactions: touch input on everyday surfaces, hand gesture recognition, and digitizing everyday passive objects into digital devices.
Most of our projects is about making a real impact. The projects like Finger Reader, Prompto, the purpose is first to develop something, show the scientific validity, talk about the technical outcome, publish papers, but we often take them outside the lab, do in the wild studies, and whenever possible leave them in the hands of people to see if what we did really made a difference. On that note, this project, the last project that I'm going to describe most bits, is about helping a deaf person to feel the music and allow them to play music. So we came up with this decoupled sensor and the display. The sensor can take inputs from surface or detect ambient sound, or can take sound from a digital input, and then it processes that sound, create the visual or vibrotactile parameters, and send them over to the display, and the display can vibrate. It has high precision vibrotactile motors as well as LEDs, and this whole process happens less than 10 milliseconds, which is very important for music purposes. We did some basic studies to understand if this can communicate some of the fundamental things. Here you can see these profoundly deaf kids. These kids are born deaf. You could see the one on the right. His task is to count the number of beats, and one in the middle, he's going to play some beats. So watch the guy on the right without looking at the guy in the middle. He's trying to detect how many beats are there. So that's one of the experiments we did. Another thing we tried was the loudness. So again, the guy with the drum is going to increase the loudness and watch the facial reaction of the guy on the right, how he feels the increase of loudness. And then we did more complex stuff. Here you can see Ashan, who has never heard a sound in his life. After a few hours of training, getting familiarized with the vibration and understanding the fundamental mapping, he's able to play. Yes, it's a very simple beat, but the point is, for someone 14 years old who has never heard sound in his life, to be able to use something, learn the audio to the music to vibrotactile mapping, and then start playing something that's going more towards a more rhythmic playing than just a random tapping, gives us a lot of satisfaction. It tells us what we are doing. Here's the science papers that we published. There's a pattern, a couple of PhDs. All of that are nice, but this is the real satisfaction. And we were so convinced. And in New Zealand, I gave it to a lady who became deaf in her late 20s. And music was something that she was missing big time after she became deaf. And we gave it to her now almost a year and a half ago, 26th March, rather early March 2019. And she has been using this since then. As we speak, she's been using, and she said she tried many things, and my deal with her is, I told her I don't need to do any scientific data collection or anything, just use it. But we would appreciate if you could share your real thoughts, your real feedback time to time. She started sharing her notebook, and this is one of the notes that I captured. And as you can see, she has started driving again, and she had turned the music up on the car and start feeling the vibration through the muscles. And she says, should have seen me. I was really dancing in the car. Probably out of the beat, but I didn't care. So that's a real statement and satisfaction of the fact that we bring science and use them and creating a meaning, creating an impact on the lives of people. Right. So those are some of the projects of many projects happening in the lab. The real takeaway message here is there is a mismatch. There is a mismatch between what the technology has to offer and our natural behavior. Don't get me wrong. The technology is really good. It's really powerful. We should continue to develop more and more its core capabilities. What I'm saying is it's equally more important to think about how do we package it for the end users. That's as important as building a new technology. Because if we don't do this, just create smart stuff for the sake of creating smart things, it could be a future like this. Just collection of smart devices doesn't make us smarter. In fact, it can make us feel disabled. When you have so many technologies and you just don't know how to use them, you feel intimidated. You feel left behind. And in that situation, technology can do more harm than good. So it's critically important that we think of these things as we do our interfaces, as we do our technologies, so that we get the full power of them. So my quest and my request is think of the technology and user interaction as well as you develop new technologies, as you develop new systems, as you develop new smart devices, because it's going to have a profound impact on the way we work, live and play, and bring the human experience into the foreground and let the technology play its part behind the scene. Thank you so much.